us to talk about moment of inertia. What do we mean as inertia? You know in physics that inertia is the tendency to remain at rest or continue the motion. And now when you see moment, you realize that it's about turning. It's about turning. Now, I have summarized everything here. Inertia is tendency to remain at rest or continuous motion in a straight line. Moment is force times perpendicular distance about a point. It is about turning around a point or axis. So we are talking about moment of inertia. We are talking about resistance to motion, starting of motion, resistance to starting of motion, or resistance to stop a motion that has been in existence. So that's what we are talking about here. And the wisest way to look about it is either you look at turning momentum or turning kinetic energy. Let's look at what I mean. Now when we talk about momentum, we consider mass multiplied by velocity. But when we talk about kinetic energy, we talk about half mv squared. And if you look at it, kinetic momentum is a vector. But kinetic energy is a scalar quantity. Therefore, but you know when we are talking about circular motion, the direction is changing continuously. So which means that the momentum cannot be considered to remain constant. So kinetic energy can be taken to remain constant in as much as V is constant. Do you understand? That is why we use kinetic energy to analyze this moment of inertia topic. Now, in circular motion, let's say this is a body of mass n. Let's say this is a body of mass n. And it is rotating around the center R. You understand? Let's now talk about this particle here with mass n. And the angular velocity is W. Angular velocity. So the kinetic energy of this tiny mass, Ke, is equal to half mv squared. Before you go on, V equals omega r. You understand? So kinetic energy for this small particle is going to be half m omega squared r squared, which you can also write as half m omega squared. Sorry, half omega squared m r squared. You know why? Omega is constant for all the particles, because I still want to consider all the particles. So I deliberately separated it like this now. Now let us now consider another particle that is here. Another particle that is here. Let's say this is M1, R1, M2, R2, M3, R3. So if we now talk about all of them, do you understand? So let's consider. So total Ke is equal to half omega squared M1 R1 squared plus M2 R2 squared plus M3 R3 squared. Infinite ad infinitum. So because of this, we cannot just say okay, M, the mass, the overall mass is what we consider we use, because the distance is also varying. Therefore, for this Ke, we are going to have half omega squared summation of what's it called? M1 R1 squared from R equals to whatever 1 to let's say 0 to the overall R. So you can see from this place to this place. So all the R, all the particles, they are put into consideration. That is where we have this expression for circular motion of solid objects. We simplify it as half omega squared m1 mr squared. Mr squared. You can see mr squared. So this summation mr squared is what we refer to as the moment of inertia. You can see mass times this. So summation mr squared from 0 to r is referred to as I, moment of inertia. Moment of inertia. So you can see this W for this body as it is moving is equal or true, but R and M for each particle varies. Do you understand? M, R, they vary. So this is what we now use to be calculating the moment of inertia of all this. You can see mass times R squared, moment of inertia. Now let's look into one or two situations. Now let's look at a situation where we can, specify about some masses and the distance from the axis. The masses and the distance from the axis. I want to find the moment of inertia. You can see because it is the distance is squared, all of them they are positive. Unlike when we are just finding moments. The clockwise moment is negative, the anti-clockwise moment is considered positive. So it's always positive. Now for this one now, we know that I, that is the representation of moment of inertia, is equal to summation mr squared. So for this distribution now, I will be equal to 2 times 3 squared plus 3 times 2 squared plus 4 times 2 squared plus 1 times 1 squared. R is the distance from the axis or points is taken. So this one is going to give us 18 plus 12 plus 16 plus 1. This is 30, 46, 47 kilogram meter square. So you can see it's very simple in this instance. But most of the time we will need to apply integration. I will treat this topic exhaustively. So before I go on, I'd like us to talk about radius of gyration. Just like we did in root mean square value. In this place, we know that I is equal to summation mr squared. So, if we know the mass, what the mass is, which is summation m separately. Are you getting it now? So, I over m, summation m, will be summation m over r summation m. Are you getting it now? So this quantity here is what we refer to as radius of gyration squared. Do you understand? Because when we are talking about moment of inertia, we cannot use the actual radius of the solid we are considering, because we have squared the quantity r. So if you sum, it's just like saying you sum r squared is equal to, and you find the square of this and you say it is r. It's not possible. Do you understand? So instead of saying, okay, now what I'm saying is this: you cannot say that summation r squared, you understand, is equal to r squared. No, there will be some error when you add all of them, like all these ones now. I add this, and I gave it like one value. No, I cannot just do that easily. Like I know that from this, for this object too, this is the radius initially. It will differ because I have brought them from different points. Just like now, if I say 1 plus 2 plus 3 plus 4, if I say 1 plus 2 plus 3 plus 4, that is 10. You know the mean now is 2.5. 2.5. Therefore, I cannot say that 1 square plus 2 square plus 3 square plus 4 square is equal to 2.5 square. That's what I've been trying to say. So that is what brought up this radius of gyration. So this is K is the radius of gyration. And you can get it by saying it is square root of I over n. It is the square root of I over n. So with this knowledge now, we'll be able to do some of our work without much explanation. Now we have this plan. Find the moment of inertia I and the radius of gyration K of a uniform thin rod about A, an axis through one end perpendicular to the length of the rod. B, about the center of gravity of the rod. Now we have a very thin rod like this. You can see. And we are told the length, find the moment, length, and okay. So I will give it length L. And since I want to find the moment of inertia about this point, about this place, I'm going to make it from L, from 0 to L. Do you understand? But before I get there, let's do this. The mass of this place, we have to find it. And the distance from this place, let's call it x. And the thickness of this small one is delta x. Do you understand? Let's take the thickness to be t. Thickness is t, very small. So this place is delta x. What is the area of this place? Let's call the breadth to be b. Let's make it b. The breadth to be b. So breadth equal to b. So volume of the volume of the small plate will be equal to delta x times b times c, which is c delta x. Now let's take the density to be rho. Density is equal to rho. So we can now say our mass is going to be c rho Tb delta x. Simple. Straight. So total mass will be equal to 0 to L rho C delta x. And by the time you do it, it's going to give you rho T B. Sorry, this is B. L. So that is for our mass. Now let's take the moment, the second moment about this space. That's what we talk about for moment of inertia. We talk about second moment. So second moment about, let's take this, y is equal to this one, okay, x squared rho T B delta x. And total moment of inertia is going to be from L, 0 to L rho T B x squared delta x. So this total moment of inertia, I will continue here. Total moment of inertia is going to be rho T B L0 x squared delta x dx. Sorry, dx. So it is going to give me rho T x cubed over 3 from 0 to L, which at the end of the day is going to give me rho T L cubed over 3. You can see rho T B L cubed over 3. But what is the mass? Rho T B L. Rho T B L is the mass. So from here, I can now say that rho T B L L squared over M over 3, sorry. So which is going to give me M L squared over 3. You can see, because I have gotten M to be rho T B L, so I removed it there. So that is the moment of inertia. Now K is equal to I over N square root, which will be M L squared over M times 3 square root. So this one is cancelled. So L over root of 3. Or you can say one, you can see it's very simple. Very simple. Now, let's do the big part. Now, from minus L over 2 to L over 2. Sorry. So, because the center now has broken it into two equal parts. So, the total length now will be considered as from minus L over 2 to L. You know, if you subtract this one from this, it's going to give you L. So, let's do it. Now, we are going to have minus L over 2, L over 2. And we are going to have this one to be x, okay, rho CB x squared delta x. So I will give us rho CB x cubed over 3 from L over 2 minus L over 2 to L over 2. So which is going to give us rho CB. This one is L, okay, over 3, yes, let me bring this one here. This one is going to be L cubed over 8 minus L cubed over 8. So it's going to be rho CB over 3. That is 2L cubed over 8. Which is going to be rho CB over 3 times L cubed over 4. Rho CB L cubed over 12. So this is our new I, if it is taken about the center. So that is the total I when it's taken about the center. And we made an observation before that. Rho CBL is the mass. So we can have it as ML squared over 12. So we have gotten that one straight. Then our K in this instance, which is radius of gyration, is going to be root of I over N, which is N L squared over 12 times N. This one cancels this. And that's going to give L over root of 12, which is L over 2 root 3. So you can say it is L root 3 over 6. Either way, so you can see the other one was L over root 3, and this time around it is L over 2 root 3. So you can see. So these questions we have solved has given us two standard results and will help us in the next topic we are going to handle under moment of inertia, and that is parallel axis theorem. It's very simple and you enjoy it. Just do it with open mind. Now, before we go on, I want you to know something about moment of inertia. When you know the moment of inertia, it means that you can calculate the circular momentum or kinetic energy, rotational kinetic energy. Like when it is in the straight line, momentum in straight line is mv, and kinetic energy is half mv squared. But when it is now in a rotational dynamics, where it is rotating, for the rotational part, that's what we are considering. M momentum is IW, that is angular velocity. KE is half IW squared. You know why I'm bringing this up? So that you will not look at it like, what's the essence of all this moment of inertia? This is where it is being used, and that should jar your interest. So you should know that when a solid object is rotating now, when it is rotating, you have to consider two things. If it is rotating and moving forward, you must consider its translational kinetic energy and what is it called? Momentum. At the same time, its rotational parts. So you can see that the energy is being used to rotate it and is being used to move it forward. So those are the things. That is where the being that conservation of energy must always be looked into. That is why all these things are calculated. What parallel axis theorem tends to do is, once you can know the moment of inertia about the center of gravity, you must be able to calculate it about any other points which is parallel to the center of gravity. Now, PP. I refer to that as PP. It's going to be M into L plus X or squared for that part. So total full I about P is going to be summation M into L plus X or squared, which is going to be summation M L squared plus summation M X squared plus summation 2L summation M X. That will be the full PP. For this one, that is just it. But when it is total, this is what it will be. And if you look at this, L is constant. The distance there is constant. So X is not disturbed, it's not changing it. So this one is going to be summation M L squared. You see? So it can still be written as L squared summation M. L squared summation M. And this one, that is what we have here. I G. Remember, when we did that of average, mean, or we talk about moments, about the CG. This one is going to be 0. Remember, what we are trying to do to find the centroid, yes, we are trying to find the centroid. We calculated what the moment about the CG or centroid will be. We realize that this one will be 0. So plus 2L into 0. So you realize that this one is going to be NL squared or summation N plus I G. So the parallel axis theorem is telling us that once we know the moment of inertia about the center of gravity, and we want to calculate the moment of inertia about an axis parallel to the center of gravity, you just take the distance from the center of gravity, square it, multiply it by the mass, and then add to the moment of inertia about the center of gravity. So you understand what I mean? So what we'll do is this. We'll take the square of the distance. We square the distance. Square the distance from CG. Multiply by mass. And then add the product to the moment of inertia about CG. That is it. Now you remember the example we just written. Here we said for this one about the CG, IDG. For this one with length L. Remember, we said it was going to be M L squared over 12. Remember, what we just calculated. Now, if we have known that as the center here, the CG is M L squared, and the distance, we want to find it about the distance of L over 2 from the center of gravity. What do we do? So let's say this is y. So I y will be equal to M into L over 2 squared, because that is the distance from the center of gravity, plus the moment of inertia about the center of gravity, so which is M L squared over 12. So that gives us M into L squared over 4 plus M L squared over 12. M L squared into 1 over 4 plus 1 over 12. So I can still continue to say, okay, let me just do it straight. 3 plus 1 over 12, which is M L squared into 4 over 12. M L squared over. So you can see now. So this one has just shown us that what we derive now is reliable. That is all. Thank you.